Let's start by comparing the definitions of a quantity versus a rate. So in mathematics, a quantity is an amount of something that can be measured. So here are a few examples. I can have 10 books, or 13 people, or 50 mosquitoes. Or I can have 100 feet squared, or 50 meters cubed. So all of these are an example of a quantity. They represent an amount of something, and we are measuring that something with different units. So the units being, in this case, books, people, mosquitoes, feet squared, so area units, and meters cubed, so volume units. So that's how we're going to measure these different somethings. Now, in mathematics, a rate is defined as a ratio of two different quantities with different units. So let's go back to the word ratio for a second. We're going to represent our ratios as fractions. So here we have a bunch of different rates, and let's double check that they satisfy the definition. So they have to have two different quantities with different units. So in this first example, I have 10 books, that's one quantity. And I have 1 year, that's another quantity, and they both have different units, so books and years. And if we want to put this into context to try to help understand the idea of rates, this might be the amount of books I can read in 1 year. So on average, I read, let's say, 10 books in 1 year. Looking at the second example, I have 150 feet squared. So that's a quantity, that's an amount of something that can be measured. We're measuring with feet squared. And then in the denominator, I have 30 minutes. So that's a different quantity measured in time. And maybe to put this one into context, maybe this is the rate at which I can paint the walls of my room. So let's say I can cover 150 feet squared in 30 minutes. And then we can have weird examples like 2 hamburgers every 1 week. So maybe that's the average amount that a college student eats, the average amount of hamburgers a college student eats per week. So 2 hamburgers every 1 week. So different quantities, different units. And then finally, something like 50 miles and 3 hours. So we have two different quantities, two different units. So I have miles and hours. And this should be a very familiar rate, miles per hour, except that it's not per 1 hour, it's per every 3 hours. So different quantities, different units define a rate. So in the type of problems that we are going to be solving a bit later, we may not be given a rate as a fraction, but there are some indicators that you're being given a rate or you're being asked for a rate. So you're being given a rate when words like per, for, and in are used. So for example, if you are given the phrase 3 pages in 10 minutes, then you are given a rate. So 3 pages is one quantity with one set of units, pages, and then 10 minutes is another quantity with a different set of units, minutes. So we can turn this into a fraction if I think about it as 3 pages in 10 minutes. So maybe that's how fast I can read a novel, is 3 pages every 10 minutes. Or 5 miles per hour. So there's that key buzzword, per, and this is, of course, a rate. So 5 miles per every 1 hour. So because it's 1, that's implied in the per hour portion. So 1 hour would be in the denominator if we wanted to write this as a fraction. And then finally, 10 bananas for $3. So my key word here is for. So 10 bananas. And then in the denominator, I would have $3. So the units here are dollars, which we could write out as a word, but we'll just shorten it and use the symbol for dollar. So a problem is directly asking you for a rate when the problem uses phrase like how fast, or directly saying what is the rate. But sometimes you're going to have to understand the units involved to understand what you are being asked for. So when you're given a rate, we should look out for these keywords. When you're being asked to find a rate, you want to look for the phrases how fast or what is the rate, but ultimately understanding the units is really going to save you in understanding the concept of rates versus quantities. Let's move on to a few examples. We want to determine if the problems below are asking us for a rate or a quantity. So we're not being asked to solve these problems. We're strictly going to answer whether or not the answer would be a rate or a quantity. And we're going to write the units of each answer. So looking at the first example, Susie read 2 books in 1 week and 5 books in 2 weeks. So let's stop there. Here in this first sentence, I have been given 2 rates. So I have been given the rate 2 books in 1 week. So there's that key word in, and there are the 2 different quantities with different units. So if I wrote this as a fraction, it would be 2 books over 1 week. And I'm given another rate, 5 books in 2 weeks. So the numerator here would be 5 books and the denominator would be 2 weeks. So that's what I've been given. So now we're going to decide what the problem is asking me for. On average, what is the rate at which Susie can read 1 book? So this one should be pretty straightforward. What are we being asked for? We're being asked, what is the rate? So this is the phrase I want to pay attention to. What is the rate at which Susie can read 1 book? So what am I being asked for? A rate or a quantity? Well, the word's right there. I'm being asked for a rate in this example. That's the first part. But now write the units of each answer. So we're not going to find the numerical answer, but we're going to focus on the units of that final answer. Well, if we want a rate, the rates that are involved in this problem so far are in units, books per week. So we're not going to focus on the numerical values. We're going to focus on the units. So in the numerator, we had the unit of books. So that's going to be the unit in the numerator, books. And in the denominator, we have weeks. That's the unit of the denominator in both rates we were given. So that's going to have to be the rate of my final answer. So books per week or weeks. All right, moving on to the second example. Gas is being pumped into a tank at a rate of h of t gallons per hour. So here, h of t is the name of some function, but we don't explicitly have the function. We just have the name of it. The name of this function is big H of t. And this function tells us rates. And the rates are in units of gallons per hour. So that's what I've been given. I've been given this name of a function that outputs rates in units of gallons per hour. So now let's look at what the problem is asking us for. How many gallons of gas are in the tank when t equals 5 hours? So I'm being asked how many gallons. That's the question. That's the key part that I'm trying to answer. How many gallons? So this is where understanding rates comes into play. I'm not being asked for a rate. I'm being asked for a quantity. How many gallons? So my final answer should be something like 10 gallons or 20 gallons, which is not a rate, because a rate would have to be a ratio. So here, this problem is asking us for a quantity. This problem is asking us for a quantity, and the units of that quantity is going to have to be gallons. So the units of the quantity of the final answer is going to have to be gallons. I don't want gallons per hour. That would be a rate. That would be like asking how fast is the gas being pumped in, or how fast is the gas being used. This question is asking how many, for an amount, for a quantity. So the units of that quantity have to be in gallons. Moving on to the next example. It takes a plane 14 hours to travel 6,000 miles. On average, how fast does the plane fly? The first thing I want to do is answer the question, is this problem asking for a rate or a quantity? So looking at the question, how fast does the plane fly? So how fast is what we want to focus in on. And how fast was one of those phrases that indicated that the problem is asking us for a rate. So we have the first part answered, but now we want to write the units of the answer. So our answer has to be a rate, If it's a rate, the units have to look like some unit over some unit, like a ratio. So now the question is, let's look back at the rate we were given. It takes a plane 14 hours to travel 6,000 miles. So what a lot of students want to do is just take the first quantity and put that in the numerator and the second quantity and put that in the denominator. But for this particular example, that doesn't quite make sense. So that's not what we can just default to every time. We have to really think about what we're being asked. So let's ignore the fact that it's a plane for a second and just think about how fast in terms of driving in a car. If I asked you, how fast are you going, and you took a look at your speedometer in your car, you would tell me, for example, that you were traveling 45 miles per hour. So when we talk about how fast an object is traveling, that rate in particular has to be distance over a time. Has to be a distance over a time. That's how we measure something like how fast or the speed of an object in the way that we know it so far is that it's going to be a distance over a time. So here, the distance traveled, the units of the distance, because remember we're trying to think about the units right now, the units of the distance are in miles. So I want miles to go in the numerator for this example. And then the units of time are in hours. So the units of my final answer is going to have to be miles over hours. So miles per hour, which should make sense when I think about how fast I'm traveling. So these problems, there's not just a, oh, so I always just do this. It doesn't really work like that. We really have to think about, in the context of the problem, are we answering it in a logical manner that makes sense in terms of the information given. And now on to the final example. A particle is traveling at a rate of v of t in inches per second. So again, I'm not given an explicit function. I'm just given the name of a function. So the name of this function is v of t. This is a rate function. It outputs rates. And those rates are in inches per second. Now the question is asking, how far is the car from its starting point? So the phrase that we want to pay attention to is how far. So this one's not asking how fast, it's asking for a measure of how far. So again, just really thinking about examples that we're used to. If I ask you, how far are you from school? You would tell me I'm 6 miles from school, or I'm 10 blocks from school. So those units of measure are going to be a distance. So here I'm being asked for just one quantity. So here I'm being asked for a quantity. And now I have to think about the units of that quantity. So here we have the units of the rate that we were given. So the units of the rate are in inches per second. And we want just a quantity that measures how far. So I wouldn't want to use the unit of time that I have involved. I have to use the unit of distance or a measurement that involves where a car, I'm sorry, this would be a typo. This should be particle if we started with a particle. So the units that I need have to do with how far something is, the particle, the car, it really doesn't matter. So here, because that unit of that distance is inches, that's going to be the unit of my answer. Let's move on to understanding the graphical interpretation of a rate. So we're going to start with something that should be familiar to you, the notion that slope is equivalent to rise over run. And then I want you to remember that we just defined a rate as a ratio of two different quantities. So here, rise over run looks like a fraction or a ratio. So graphically, I want us to think of a slope as a rate. So let's go ahead and take a look at this particular example. So before I look at the graph, I want to define what I graphed. I defined a function called h of t. And h of t is going to represent the height of a tree in feet after t years. So this function h of t allows us to plug in years into it, and what it's going to output is the height of a particular tree in feet. So this function, it's not perfectly straight, but we're going to use our imagination and say this function is linear. And the input variable has to be t for years. And the output variable is going to be feet for the height of the tree. So h of t is on the vertical axis, t is on the horizontal axis. We're not talking x's and y's because we're talking about a specific example. So now I want to analyze the slope of this particular linear function in the context of how we labeled the units on the axes right now. So if I go ahead and choose 2 points on this line, so I want to choose 2 points that go through whole number coordinate points. So I'm going to choose this one right here, and again, it's not perfect, but I tried to draw it so that we go through the point 1, 4, and then through the point 2, 7. So I want to focus in on any 2 points because this is linear. The slope should be the same between any 2 points that we choose. So if we were to try to find the slope of this line given this graph, we're going to think rise over run. So we're going to think, well, how many units do I go up and how many units do I go right? So in this case, let's go ahead and see how many units I go up. So I'm going from 4 to 7, so a total of 3 units. But notice I've been generically saying units, and I have unassigned units associated with the vertical axis. So if I ask for the slope of this particular function that's in the context of a problem with labeled units on the axes, I can add a little bit more information about the slope. The slope is going to be 3 feet, so that's my rise. 3 feet, I go up 3 feet, and then I'm going to move to the right 1 unit. And the units on the horizontal axis, if I go from right to left, is going to be in years. So since it's going to be 3 feet in 1 year. So what we just found by analyzing this linear function, the slope of this linear function, is we found a rate. We found the rate at which the tree grows between 1 and 2 years on average. So between year 1 and year 2, this tree grew at a rate of 3 feet in 1 year. And because this is a linear function, we know that this tree grows 3 feet in 1 year for every year that has passed. But this was just a completely made up function and made up situation. But I want you to get from this the notion that a slope equals a rate when we put it in the context of a problem and studying and understanding the idea of units. So we can also analyze this graph for particular heights. So just looking at the function values, for example, so this function was called h. So if I analyze h of 3, for example, well, h of 3, if I go up to the function at 3, the output value is 7. So what that means, h of 3 equals 7, by just analyzing the actual linear function, not the slope, just the points on the graph, h of 3 equals 7, well, that means at 3 years, the tree is a height of 7. So the tree is 7 feet tall. So there's a lot of information we can draw from the graph of a function. Previously, this portion here, this is a pre-cal or prior type of question, just what do points on the graph mean? Now we're going to start to analyze the slopes. What does the slope tell us in terms of the given problem? Now I want to focus in on the idea of units. So what I want to start with is comparing linear units, square units, and cubic units. So here's an example of each. If I have the unit of feet, that's considered a linear unit because it literally measures something like a line. So we can go and say that this line is, let's say, 3 feet long. As opposed to square units, an example of that being feet squared, and square units come from finding area. So let's say now I wanted to find the area of this rectangle, which had a base of 2 feet and let's say a height of 3 feet. So the square units are coming from the fact that to find the area of a rectangle, we measure base times height, so 2 feet times 3 feet, and we multiply the numbers together. That's where the 6 comes from. But the unit feet squared come from the fact that I have feet times feet. So 2 copies of feet become feet squared. Just like the variable x. X times x becomes x squared. Well, we could think of feet times feet becomes feet squared. So because the base and the height have the same units, that's where feet squared, or these square units, are coming from. So similarly, feet cubed come from finding volume. So now I will try my best to draw a nice three-dimensional figure. So now let's say this prism here has this width of 2 feet and this depth of 3 feet and a height of 4 feet. So if I were to find the volume, I'm going to do length and width and height. So I'm going to multiply 2 feet times 3 feet times 4 feet. And again, all the numbers multiply together, and that's what gets us 24, but the cubic units come from the fact that I have 3 copies of feet, or feet cubed. But all of these examples had all the same units as the base and the height measurements. But now let's go ahead and change it up. Let's see what happens if I still try to find area, and now I have 2 different units for the base and the height. All right, let's focus in on if I have a height of 4 inches and a base of 2 hours. Now I know what you might be thinking, how can I label the base of this rectangle as 2 hours? But just try to go with me for a second on this. So let's say I was trying to find the area of this rectangle, and what I know is that the units are hours. So don't think about it as time, just think about this as just one variable, and then inches as another variable. So if I were trying to find this area, well, I know that I can set it up the same way I did previously, 2 hours times 4 inches. And I know what to do with the numbers, I multiply them. So 8 comes out as the numerical value, but now what do I do with hours and inches? I can't convert one into the other so that I end up with the same units. And when I had feet times feet, well, that was 2 copies of the same thing, so I ended up with feet squared. Well, in this example, all I can do is end up with hours times inches. And I know that that's weird and I know that it doesn't make sense, but I want you to just try to understand where the units are coming from. The fact that we're multiplying the base times height, and those numerical values come with the appropriate units. So now I'm going to throw in one additional thing that makes it different as well. If I go ahead and label the height as with a unit that is a rate. So let's say this height is 4 inches per hour, and this base is in hours. So I know, really weird. So I'm going to have 2 hours times, so here's what's going to change on the right. So on the right hand side, I'm multiplying 2 hours times 4 inches per hour. All right, really weird, I know. So the 2 and the 4 get multiplied together to become 8, and now I just take the units and I multiply them. Well, I have hours times inches per hour. So let's notice something here. I have, this is like hours over 1 times inches over hours. So hours and hours, these are the same units, right? Hour, hours, it doesn't matter. It's the same units, one in the numerator, one in the denominator. So I can cross cancel. And I'm going to end up with just 8 inches. I'm going to end up with 8 inches. So I'm multiplying the units together, and in this last example, the 2 cancel each other out. There's one in the numerator and one in the denominator because the units of this vertical portion here are units of a rate, inches per hour. Alright, so moving on. Now we want to understand units on a graph. So we did that whole little side note on units because we want to be able to understand units on a graph when the axes have different types of units. So let's say this function here is called v of t. So I'm going to go ahead and say it's a linear function v of t. And we are at times going to be interested in finding the area of a particular region that has to do with this graph. So let's say this region right here. I'm interested in finding the area of this trapezoid. Alright, well, here's what I know. I know the numerical base of this trapezoid is 4 units, and then I can find the first height and the second height, and so I can find the numerical value for this trapezoid. But I want to be able to understand what this area represents. So area, even though this is a trapezoid, area is still found by base times height units. So the base of this thing has units that are hours, and the height of this thing has units that are miles per hour. So this height is in miles per hour, and this width down here is in hours. So if I'm asking for the area of this green region here, what does the area represent? This area is going to represent whatever miles times hours leaves us with. So now let's go ahead and do that. If I have miles over hours times hours, well, notice what happens is that this is like hours over 1. I'm multiplying fractions here so I can cross cancel. The hours cancels out and I end up with just miles. So if I were asked to find the area of this green region, I can find the numerical value. At this point, that's geometry, just knowing the area of a trapezoid formula. I can find that numerical value right now. But I want to understand in the context of this problem what this area represents. So that means I have to understand the notion that area is base times height. Well, the base units, hours, times the height units, miles per hour, leaves us with just miles. So when we find the numerical answer, we're going to tack miles onto the end of it as the entire answer. So it's not just the number anymore, it represents a specific number of miles because the units matter. So let's try one more. Let's say this function here represents painting again. Let's call it P of T, because the units on the vertical axis are feet squared per minute. So up and down, these units are feet squared per minute. And then on the horizontal axis, this is minutes. So now this is, if I am asked to find the area of this linear function, this is similar to the last one, in that if I'm asked to find, let's say, the area of now this purple trapezoid, again, I should be able to find the numerical answer to the area of this trapezoid, just the base plus, or 1/2 the base, or 1/2 the height, base 1 plus base 2, right? That's just a formula. I'm asking us to understand what that area represents in terms of the context of the problem. So I'd have to multiply the base units being minutes, and again, the height units being feet squared per minute. So if I multiply feet squared per minute times minutes over 1, notice what cancels is the units of minutes, so what's left is feet squared. So if P of T represents the rate at which I can paint the walls of my room, this area here represents how many feet squared, how much area I actually painted between 3 and 6 minutes, because I took this area between 3 and 6. So right now, it's more important for you to understand, if I were to just give you a rectangle and tell you, like we did in those previous examples, if I were to just give you a rectangle and tell you the units of the base is 3 hot dogs and the unit of the height is 5 cats, that you tell me the area of this rectangle is 15 hot dogs times cats. And I know that that's weird, but I need you to get past using typical units and using typical variables like x and y, and using just those really familiar algebraic expressions, because we're going to start looking at things that are a little bit different that happen in the real world. Not that we ever multiply hot dogs times cats, but just to get past the really, really common things like just feet, or feet squared, or feet cubed. Alright, so now it's time to jump into a couple of examples. So all of these examples are actually problems from Algebra 1, Algebra 2, and Precalculus books. So none of these are actual calculus problems. They're all problems, though, that involve rates of change and allow us to graph the function to really try to analyze the slope as a rate. So here, this first example, we have an 8-inch tall candle burns at a rate of 2 inches per hour. The candle's height is modeled by the function h of t equals 8 minus 2t. So let's stop. My first recommendation for word problems is read them twice. So again, an 8-inch tall candle. So we have this candle, it's 8 inches tall. It's burning at a rate of 2 inches per hour. So every hour that passes, 2 inches of this candle is gone. The candle's height is modeled by the function h of t equals 8 minus 2t. So now let's go ahead and take a look at the questions that were being asked. Part A. Why is the variable a t instead of an x? So this first question is really just to get you thinking about the problem. So we can use any variable we want. But why is the variable t used? Well, the variable t is used because t stands for time. So simply because t stands for time. And then that will help us remember that when we have to substitute in something for t, that it's going to have to be in the units of hours, because that's the only unit of time that we have in the problem. So this is going to have to be a units in hours. So now part B, graph the function by hand. What is the domain and range of the function h of t? So here let's go ahead and graph this function. We have 8 minus 2t. So t is the variable on the horizontal axis. So t is my variable on the horizontal axis. So h of t, the height function, is on the y-axis. So just to sort of help you remember this, so we have h of t equals 8 minus 2t. Now if your familiarity is with y's and x's, then what you can think about this is as y equals 8 minus 2x. So if you want to think about it as y equals 8 minus 2x, well, x is on the horizontal axis. So since x and t correspond, that's why I put t on the horizontal axis. And then h of t is the same as y, and y goes along the vertical axis, so that's why I went ahead and put h of t on the vertical axis. I'm also going to put my units there. So on the horizontal axis, I have time, which was in hours, and then on the vertical axis, I have h of t. So h of t is the candle's height. So what are the units of height? We look to inches. The units of height here are inches. So vertical axis units are inches, the horizontal units are in hours. So if I were to graph this 8 minus 2x, I hope in this format you can recognize that this is a graph of a line. So the y-intercept of this line is 8. So I'm going to go to 8 and draw my y-intercept. And the slope of this line is negative 2. So I'm going to go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And I'm going to go ahead and connect the dots as best I can in a straight line. Alright, and I'm going to stop right there. What is the domain and range of h of t? Now, here's something to be really cautious of. If I asked you to graph y equals 8 minus 2x, then you would actually go ahead and continue this graph past the y-axis over here. So I'd go to the left of the y-axis and I would make sure to draw arrows on both sides, because that line would continue on and on and on forever. But I'm asked to draw h of t equals 8 minus 2t, which represents something in the real world. So it represents the height of a candle. Whoops. So let's go ahead and erase this. And what I want to think about is on this t-axis, why did I stop at x equals 0? So why can't I continue over here and go up to and left 1 and continue the graph over here? Well, I can't do that because over here, if this axis, this horizontal axis represents hours, well, right here at the origin, that's 0 hours. Once I go to the left of 0, now I'm talking about negative 1 hours. I cannot have negative time. So I'm going to go and erase that portion. The actual graph itself here is going to start at time 0. So I'm going to have to go up to the function at 8 and have that filled in circle that I originally put down as the y-intercept. That's the start of the graph. I can't go to the left of it. And then my graph represents this candle burning. So the candle's going to burn all the way down to this height of 0. So remember, this vertical axis represents height. And so at 4 hours, that's when the candle's going to reach this height of 0. So if I go anytime past 4 hours, so I cannot continue the graph down here because then this graph would have negative height. And we know that can't happen. The candle will just stop and burn out after 4 hours has passed. So what is the domain and range of this function? So remember, the domain we think of as the x values, or in this case the t values. What values can I plug in? So the values I can plug in are only from 0 to 4. So the domain of this function are from 0 to 4. So I can plug in 0, I can plug in 4, so I include closed brackets. And the range is what's the height that's going to come out? Well, the smallest height that this candle can be is 0. It can have a height of 0. It can burn all the way down to nothing. And the tallest this candle can be is what it started at. So it started at 8 inches tall, and if you'll notice the graph, that's the highest h value I can take on. So the range is from 0 to 8. So if you wanted to graph the function as y equals 8 minus 2x, that's fine, but you would have to stop and think about the real world situation that's happening and the fact that we would have to restrict the domain between 0 and 4 because it doesn't make sense to have negative time, so I can't go this way, and I can't go down because it doesn't make sense to have a negative height to the candle. So now let's look at the part C. Explain why the slope of the line is negative in the context of the problem. So why is the slope of the line negative? Well, let's go back and look at the first sentence of the problem. An 8-inch tall candle burns at a rate of 2 inches per hour. So when we think about a candle burning, the height of the candle, well, the height is going down. The height is getting shorter. So when we think about going down or getting shorter, we should think about this negative concept in math. So that's why the slope of the line is negative. So as I read a graph from left to right, the slope is negative, so this function is decreasing, right? So the height of the candle is decreasing. We think about the slope as rise over run, so we go down and then to the right one. So why is the slope of the line negative? Because the candle's height is decreasing. So negative slope, we're thinking decreasing. Now part D, how tall is the candle to begin with? How tall is the candle to begin with? So when you see this phrase, to begin, we should think about a time. So to begin, time is going to be at 0. Now, the question isn't asking for a time. The question is asking how tall. So my units are going to have to be some unit of distance, right? How tall, or some unit of measure. So how tall is the candle to begin with? How tall is the candle at time 0? So at time 0, at 0 minutes, where is the function? So let's go ahead and just use a different color. The function is up here at 8. So how tall is the candle to begin with? It's 8 inches tall, which can also be read in the original first sentence of the problem. An 8-inch tall candle burns at a rate of 2 inches per hour. So it starts out at 8 inches. Now, how tall is the candle after 1 hour has passed? We can do this in 2 different ways. Now, we can recognize that we're searching for how tall. And this nice function, h of t, is a height function. And it's a height function that allows us to substitute in values for t times and get out heights. So our value for t that we would substitute in is 1. And 1 is in terms of hours, so we could substitute 1 into t and find h of 1. So 8 minus 2 times 1 is 8 minus 2, so 6 inches. So I substituted in 1 hour and I got out 6 inches. So my function, right, functions are I can substitute something in and then math stuff happens and then the number comes out. Well, the function also changed the units, so that math stuff includes changing the units. So I substituted in hours, math stuff happened, and I got out inches. Or once you have the function graphed, the nice thing is that I can go ahead and look at, well, at 1 hour, where is the graph? The graph is at a height of 6. So the answer to part E is going to be 6 inches tall. So how tall is the candle? I want a height. My height has to be a unit of measure, so it has to be in inches. And then part F, when does the candle burn out? Hint, when the height of the candle is 0. So when does the candle burn out? Well, a candle is going to be burnt out completely when its height is 0. Now that's not the answer. The answer is not when the height of the candle is 0. This question is asking when. It's asking for a time. So I'm going to need a t equals. So here, if I look at the height of the candle at time 0, it's 8 inches tall. At time 1, it's 6 inches tall. At time 2 hours, it is 4 inches tall. So in other words, at what time is this height going to go all the way down and reach 0? At 4 hours. So at t equals 4 hours, when does the candle burn out? At time 4 hours, when the height of the candle has reached nothing, when it is now all the way down to 0. So this first example is actually taken from an Algebra 2 book, and it's a really great example of a linear function, and it's easy to graph by hand. It goes over two different types of problems that go ahead and ask you to substitute in a value. So going to substitute in 1 into the time and get out a measure in inches, and then also asking you to sort of work backwards and asking you for a time if you want a specific height. So this is a really great problem to have to think about. It's a really basic problem that if you feel like you still need help and you're still struggling with it, I would definitely come and ask for tutoring, absolutely, before we get into some actual calculus problems. Alright, so this last problem is a little bit different. So the problem tells us how fast a cheetah runs is modeled by v of t equals 30 cosine pi over, whoops, that's supposed to be a t plus 2, where t is in the interval from 0 to 20 seconds, and v of t is in feet per second. So let's read it again. How fast a cheetah runs is modeled by v of t equals 30 cosine pi over t plus 2, where the time frame I care about is only when t is between 0 and 20 seconds, and what I will get out, v of t, is in units of feet per second. So I substitute in seconds, and instead of getting out a quantity, I get out a rate. So I get out how fast the cheetah is going at any particular moment in time. So the units that I get out are in feet per second. Now, this function, I wouldn't expect you to know exactly what it looks like necessarily by hand, but it's going to be important that you have a general idea of what's happening with this function, because we want to graph it in an appropriate viewing window on the calculator and then sketch it. So before we even jump to the calculator real quick, let's take a look at this original parent function, the cosine function. So what we should know about cosine is that it oscillates between -1 and 1. Except that this 30 in the front is the amplitude of the function, which changes what the function oscillates between. So now it oscillates between 30 and -30. So on my calculator, that affects the y min and y max. So I'm going to remember to change the y min to -40 and the y max to +40 so I can see the entire graph. And then this part here is kind of nice. It tells us that our t values, or our x values, our x min and x max, are going to be from 0 to 20. Those are the only times that we care about. So let's go ahead and jump to the calculator. Alright, so under y1, I'm going to enter 30 cosine pi divided by, and in the denominator we had the quantity x plus 2. So that needs to be in parentheses. So I'll close the parentheses of x plus 2. Then I'll close the parentheses of cosine. And then before I even hit graph, I'm just going to go to window, because I know I need to change. X min, I've already set it for us, but just to remind you, x min is 0, x max is 20. And then we said our y min and y max were -40 and 40, so we could see all that oscillation happening. So now I'm going to go ahead and hit graph. So here is the graph of my function, and only between 0 and 20, the only portion of the graph I was told I needed to worry about, between 0 and 20. So at 0, that's how fast my cheetah is starting, and then it continues to get faster and faster as we move along. Alright, so now let's go ahead and graph it based on what we saw in our graphing calculator. So we'll just do a rough sketch here. So time 0, it started somewhere on the y-axis, and then it kind of curved out like this. So that's just a rough sketch of our graph. Now, part B, what are the units of t? So we talked about this. T is in the interval from 0 to 20 seconds. So the units of t are in seconds. But what's different about this from the last few problems is the units of v of t. So notice our function takes in seconds and it turns them into an output of v of t in feet per second. So if we take a quick second to think about the previous problems, when we had the candle, well, what happened was we plugged in hours and we got out a height in inches, right? So we plugged in a quantity and we got out a quantity. So now in this last problem, we're plugging in a unit of time again. We're plugging in seconds, but the units that we're getting out aren't also a unit of quantity. It's a rate. I'm getting out feet per second. So at a particular time, we're going a particular speed, or the cheetah is going a particular speed. So for part D, how fast is the cheetah running after 1 second has passed? So here on my t-axis we have seconds, and on my vertical axis I now have a rate. I have feet per second is on my vertical axis. So the question is, how fast is the cheetah running after 1 second has passed? So it's asking for, what's this output? What's this y value, or this v of t value? So for part D, what I'm being told to do is substitute in the time, 1 second, into this function v. So v of 1 is cosine, whoops, forgot the 30 cosine pi over 1 plus 2. So it's 30 cosine of pi over 3. We should be able to do this by hand. This would be 30 cosine of pi over 3 is 1/2. 30 times 1/2 is 15. And my units are going to have to be in terms of a rate, so feet per second. So v of 1, the units of any v of t for any time t have to be in feet per second. So after 1 second has passed, this cheetah is running 15 feet per second. So part E should be pretty quick. How fast is the cheetah running after 3 seconds has passed? So we're just going to go ahead and substitute 3 in for t. So we're going to evaluate v of 3. So 30 cosine pi over, and we're going to have 3 plus 2. So we're going to have 30 cosine pi over 5, which is not one of the values on the unit circle. So we don't know what this is exactly, so we'd have to do it on our calculator. So I'll tell you that it is about 24.271, again, feet per second. So this cheetah is picking up speed pretty fast. So at 1 second, it's going 15 feet per second. And after 3 seconds has passed, it's running 24.271 feet per second. So now, part F, when is the cheetah running 25 feet per second? So we do not take 25 and plug it into t, right? 25 is a rate, 25 feet per second. So I can't substitute it in for a time if it's a rate, but I can substitute it into v of t, which is a rate. So what we have to do is let 25 equal the function itself, 30 cosine pi over t plus 2, and solve for t. And we're going to solve this in the same way we did the last one. We're going to graph y2 as 25, and we already have this first function as y1, and we're going to find its point of intersection. So let's jump to the calculator. Alright, so let's go ahead and enter our y2 as 25, and we're going to go ahead and hit graph. So we want to know when these two functions intersect. They clearly intersect at this point here. So to find that point, we go to second trace, 5 for intersect. And we're going to go ahead and move towards that point of intersection on the first curve. So right now I'm on the curve, the cosine curve, and I'll hit enter. Now I'm on the straight line, and I'm going to hit enter, enter again. So when does the cheetah reach 25 feet per second? At 3.363 seconds, or if we want to round, 3.634 seconds is exactly when the cheetah is going to reach that speed of 25 feet per second. So 3.364 if we want to round. So to conclude, we're going to say at a time of 3.364 seconds, that's when the cheetah is running 25 feet per second.